So continuing where we left off, we were talking about permutations, and then we talked about the fundamental counting principle. The last one that we're going to talk about is something called distinguishable permutations. And traditionally, the way I'm going to ask this question is always going to be with some word, like for example, peep, and I want to know how many ways I can arrange the letters in the word peep. That would be distinguishable, right? But I could tell a difference between the two. So, for example, if I just had the word peep, and then here's the word peep, and then I said, okay, I'm going to switch the two E's. That's not making a new word. That's not distinguishable. So I only want to count that once, not twice, even though theoretically I could be switching the E's. If I had a word like math, and I was doing this, this would be a factorial problem. There are 4 different letters, and I want to know how many different ways that I can arrange all 4 letters. So the answer would be 4 factorial, which would be, if you remember right, 4 times 3 times 2 times 1, which is 24. Okay, we are not dealing with the word math here, where there are no repeated letters. In this case, we're dealing with the word peep. So I'm going to go ahead and list them, and then we're going to talk about the different mathematical ways to do this. If I want to know how many different ways, obviously I would start off with the word peep, P-E-E-P, but then I also have pepe, as well as P-P-E-E. Yes? So there are 3 different options so far. Those all start with P. There's no other ways I could have P as my first letter, right? Because I have the second P is the last one, the second to last one, and then the second letter. So now I need to start with the letter E, so I would have E. This is so much fun. And then I have F. And then my last one would be epi. And there are no more. You could try to think of them if you wanted to, but you would come up empty-handed. So that is obviously the long way. Now, in the next example, we're going to have the word Tallahassee. And obviously, that would be a much different type of problem. There would be no way to do this and list all the different options of distinguishable permutations. We're going to look at a formula for this. Here is the formula for calculating distinguishable permutations. It's n factorial divided by s1 factorial times s2 factorial times as many of those s factorials as we need. Now, what does it all mean? N is going to represent the number of letters in the word. And what S1 or S2 or any of the S's represent is the number of times a given letter is repeated. I'm not going to write that out, but once again, each of the S's represents a number of times any given letter is repeated. Let's look at the word peep one more time. We know what the answer was. It was 6, but let's see if we can get that using the formula. In total, there were 4 letters. So it'd be 4 factorial. And then the letter P was repeated twice. And the letter E was repeated twice. So it'd be 4 factorial over 2 factorial times 2 factorial. It's going to be really common that people make a mistake with this. If you want to, and I don't suggest this, but if you want to type that all in one line and push enter, make sure you put parentheses around your denominator. Otherwise, you'll get the answer. My suggestion is to type in 4 factorial, and 4 factorial is 24. And then type in the denominator, 2 factorial times 2 factorial. We should know what each of those are, because 2 factorial, remember, means 2 times 1. Our denominator is just essentially 2 times 2, which is 4, giving us an answer of 6. So let's look at that with the words Miami and then Tallahassee. Miami has 5 letters in it. It would be 5 factorial. And then the letter M is repeated twice. And the letter I is repeated twice. The letter A is repeated once, and you could do 1 factorial in your denominator as well, but it's obviously unnecessary. That would just be multiplied by 1. So my numerator here, we've already done 5 factorial, it's 120. We know that 2 factorial is 2, so 2 times 2 is 4. We'd have 120 over 4, which would be 30. So that would be our answer for A. Our answer for B is going to be a little bit more complicated. Just so you guys know, I've told you guys about the permutations button on your calculator as well as the factorial button on your calculator. There isn't an option for permutations with repetition on your calculator. You just have to kind of type this, something like this, into your calculator. All right, Tallahassee, how many letters we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'd be 11 factorial over, letter T is not repeated, and I don't have to worry about it. The letter A is repeated 3 times. The letter L is repeated twice. There isn't a repetition of the letter H. S is repeated twice, and E is repeated twice. So I'm going to go ahead and use my calculator for this one. 11, remember the factorial button is found under Math, PRB. 11 factorial is, remember, I'm not encouraging you to type this all in one line in your calculator. 11 factorial is 3991680. And then 3 factorial is 6 times 2 times 2 times 2 over 48. 3991680 over 48 is 831,600, 831,600. And so that would be permutations with repetition. So far we have covered the fundamental counting principle, which remember is an example. You have a certain event that you can select in n ways, and you have another event that you can select in m ways. You just multiply those, and that's the number of ways. Then we had factorial. Factorial said, if I have n objects and I want to know how many ways I can arrange all n of them, that would be factorial. You just take whatever that number is, and you do the factorial of it, and that would be your answer. Then we covered permutations. Permutations is in a case where order matters. So that example that we looked at is we had 10 students, and we want to select 3 of them and give them different prizes. Okay? The order in which, like first place got more than second place, got more than third place, so the order matters. That's what makes it a permutations problem. 10.2, we're going to cover combinations. Combinations would say, hey, I'm going to give the top 3 finishers $1,000, right? The order there doesn't matter. You don't care if you're first or you don't care if you're third because you're getting the same prize. But with permutations, the order of those top 3 are important. That makes it a permutations problem. And lastly, we covered this distinguishable permutations, which would be something like rearranging the letters in a word where there are repetitions of any given letter in the word. So that's 10.1. Have fun out there.